Hello my people, I hope we're doing well today. In these videos we'll be sort of stepping back and reviewing sequences and series, and more specifically Sigma notation and the summation formulas that accompany it. Now, some of that verbiage doesn't sound familiar or you don't remember it, then this is the video for you because I'm going to explain it all. Now, in class we talked about how Riemann sums oftentimes have a pattern. And those patterns make those Riemann sums into what are called series. And because they are series, we can use all of those cute little formulas and methods to calculate those sums that we would use for a regular series. But if you're thinking series, I don't remember that stuff, then let's go ahead and back up. And not to get ahead of ourselves, let's just start with sequences. Now, sequences are just lists of numbers with a discernible pattern. So this is basically what's important right here, okay? A sequence is a list of numbers with a discernible pattern. A list of numbers without a discernible pattern is still a list of numbers and may indeed be meaningful mathematically, but it is not a sequence. The whole idea of a sequence is the fact that because it has a discernible pattern, we can actually work with it analytically, meaning we can find a model for it. We can put it into notational form, okay? Now, I will tell you that a sequence or a series can also be composed of variable expressions, but that's something way down the road. So that's a tomorrow calculus student problem, okay? But for right now, we're just going to do a very brief review of sequences and series, specifically for the sake of being able to use the Sigma notation to help us calculate or evaluate the sums represented by the Riemann sums, the area approximations under the curve. There are a lot of things about sequences and series that we will not cover, we will not review. We'll sort of punt those down the road, and we'll deal with those, or you will encounter those in Calculus 2. All right. Now, when we're talking about, and this video is going to be, towards the beginning, a little bit more of me just talking, and the actual working of problems will be a little bit later in this video, or perhaps in the next video, because there's just a lot of conceptual stuff that needs to be talked about, okay? Now, some of the easiest of the sequences that we know of is whole numbers, so 0, 1, 2, 3, 4, there's a pattern there, right? Perfect squares, 1, 4, 9, 16, 25, multiples of 3, unit fractions. Now, those lists of numbers have a discernible pattern, and like I said, we can model them. So anytime you hear a math teacher or reading a math book about modeling, basically what that means is turning something into notational form so that I can work with it analytically, okay? Now, we need to recognize that sequences are functions. That's basically the first thing that needs to be understood. And it's just functions where the inputs are positive integers, because the inputs are basically referring to the position that a particular number has in the sequence. So you can have a first term, you can have a second term, but you can't have a 3.5 term, you know. So basically, they are functions, meaning that each input, meaning each position, has exactly one output, one value to every position. That means it's a function. It's just a very weird function, okay? They have only positive integer or natural number as their inputs, usually starting with 1. Now, because they wind up being different in nature than regular functions, we usually use a different variable, meaning instead of x, we're using n, or sometimes k or I. But usually not x, because x is reserved for functions. And so even on your calculator, you'll notice that if we actually go to the mode right here, and we go down, and we go on over here to sequences, right? And we click on it, and then we go to y equals, we have basically u of n and n. Basically, the variable becomes n. And if you go back to the main screen and you just hit this variable button that you're used to using for x, it'll be n. Okay? So n is there as sort of this, as just the indication that we're dealing with sequences or series. Now, because we can model these things, let's actually walk through the 4 examples that we had up at the top of the page and actually model them, right? What we see here is that for the whole numbers, the first position is not a 1. The first position is a 0. And the second position is a 1. The third position is a 2. The fourth position is a 3, meaning that the value seems to be 1 behind its position number, meaning that your a sub n, so a sub 1, a sub 2, a sub 3, a sub 4, wind up being 1 behind, minus 1, the n, the position number that you're inputting. For the perfect squares, 1 happens to be 1 squared. Position 2 happens to be 2 squared. Position 3 happens to be 3 squared. Position 4 happens to be 4 squared. And because of that, the model that I use, the a sub n that I use, is n squared. Multiples of 3, first position is 3, or 3 times 1. Second position is 6, or 3 times 2. Third position is 9, or 3 times 3. And the fourth position is 12, or 4 times 3. So therefore, the nth position is 3 times n. And these down here are called unit fractions, okay? Just basically meaning that there's always a 1 in the numerator and always an integer, or a positive integer, a whole number, in the denominator. But because the first one is 1 over 2, and that denominator is a 2 in position 1, the denominator here is 3 in position 2. The denominator here is 4 in position 3, sort of in an analogous fashion, but obviously in the reverse way. That 0 wound up being the first position here, wound up giving me a minus 1. 2 being in the denominator here in the first one means that our a sub n is 1 over n plus 1. Now, if that was kind of a little bit fuzzy, that's fine. We'll continue to work on that stuff. But for right now, we need to just understand that that's what's going on more than being able to actually execute it ourselves. So, we could extend our exploration of sequences, but that's all we really need in order to move on to series. Now, what is a series? Well, a series is simply a sequence with the commas replaced by addition signs, meaning that a series is the sum of all the members of a sequence, or a sum of numbers with a discernible pattern rather than a list of numbers with a discernible pattern, right? A sum. Now, it is possible to express many of the series that we encounter longhand, right? Meaning that you can actually list them out, as a really long sum. But we use what is called Sigma notation to shorthand the sum of terms of a sequence, using the same a sub n, the same analytical model that the sequence use. We just plop it into a sigma notation, and we'll talk here just a second what it means, okay? So if we have the following sequence, 1, 3, 5, 7, 9, 11, and we discern the fact that that is a sequence that basically, for every a sub n, if you plug in, so if you want the fourth term, you can go ahead and plug in 4, and you will get 8 minus 1, or 7, right? And on and on and on and on and on. Now, I don't want to go over, arithmetic sequences and the formulas and everything like that. We just need to go ahead and understand that when we are asking for the series, we are replacing this with this. And all that you need to know for sigma notation is that's what this means. What this means is sigma, being the Greek letter that's equivalent to our letter S. And the reason that they use sigma is that we are dealing with a sum, S, sum, sigma, S. There we go. And what this means is the sum of all of the terms that have a form of 2i minus 1. And notice that I've replaced n with I here. Sometimes just And the choice of the variables here is really immaterial, okay? This is the sum of all of the terms that have the form 2i minus 1 from I is equal to 1 to I is equal to n. So this is basically the number down at the bottom is the start of the interval, and the number on the top is the top of the interval. Since this, of course, is the first 6 terms, this, instead of going to n, if you wanted to just have the first 6 terms and not worry about the and it keeps going part of it, it would just be that. It would be sigma I is equal to 1 to 6 of 2i minus 1 instead of from 1 to n, right? And so basically there are finite sums that you can use your sigma notation with. What you'll find out later is there are infinite sums that you can use your sigma notation for, and this is sort of indefinite, right? You don't know whether you don't know what n is. You're sort of leaving n open for, all possibilities, okay? That's really neither here nor there, but you need to understand why this sigma notation is the representation of those first 6 terms. So let's do a little bit of practice. Now, in Calculus 2, you'll be asked to entertain infinite series on a regular basis. It's called Chapter 11 in your book, okay? But our unit on Riemann sums will focus primarily on finite sums. So let's suppose that we're asked for the sum of the first 8 terms of the series above. Now, of course, I showed you what it looked like to find the first 6. So this one right here, if I'm looking for the first 8 terms of the form 2i minus 1, then what I need to do is I simply need to start plugging numbers in, right? I need to first plug in 1. So this winds up being 2 times 1 minus 1. And then I need to plug in 2. So it's 2 times 2 minus 1. And then I need to plug in 3. So it's 2 times 3 minus 1. And then I need to plug in 4. So it's 2 times 4 minus 1. And then plug in 5. And so it's 2 times 5 minus 1. And then it's 2 times 6 minus 1. And you're thinking to yourself, my gosh, even 8 terms is becoming a little bit annoying, right? And you'd be right. You're not wrong about that, okay? And what that winds up being is 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15. And what that adds up to is 64. And if you don't believe me, go ahead and just add it all up yourself, okay? Now, the same thing can be done for something like this, where it's runs from 1 to 6, and your a sub I, or when we're dealing with a sequence, your a sub n, basically your analytic model is 3 minus I squared. So really what this is asking for is the sum of the first 6 numbers fitting the pattern 3 minus I squared. So let's go ahead and do it. So we have 3 minus 1 squared plus 3 minus 2 squared plus 3 minus 3 squared plus 3 minus 4 squared plus 3 minus 5 squared plus 3 minus 6 squared. And what that winds up being is, this one winds up being 3 minus 1, or 2, 3 minus 4, or negative 1, 3 minus 9, or negative 6, 3 minus 16, or 3 minus 16, which is negative 13, 3 minus 25, which is negative 22, and 3 minus 36, which is negative 33. And just in case you're wondering, that adds up to negative 73. Okay. Now, your calculator does do sigma notation, so let's go ahead and let's actually check our answer for this first one. It's in the same menu that you use to get your derivative. So if you go second f or alpha f2, and notice that number 2 right here is summation, and you're going to get a sigma notation. Now, it doesn't really matter what variable you use. I'm already in sequence mode, so I'm going to actually get an n when I push the variable button. But if you hadn't switched over to sequence mode and you were still in function mode and you pressed x, it would be the same thing, right? So I'm going to go from 1 to 8, and then it's going to be 2 n minus 1, enter. And that's 64. And let's go ahead and confirm the second one right here, okay? I'm going to go alpha F2 again, press 2, and I'm going n is equal to 1 to 6, and it's going to be 3 minus n squared. And I get negative 73, okay? So actually on the, if I were to assign you a worksheet, you actually wouldn't need an answer key for the worksheet. What you would really need is just to check your answer that you've worked out using your calculator, and that will basically be your solution manual, so to speak, okay? Now, if you're thinking to yourself, gosh, that's really burdensome, what happens if it becomes more than 6 or 8 terms? Yes. And this brings us to our buddy Carl Friedrich Gauss, okay? Now, let's suppose we're asked for the sum of the first 60 or 80 terms rather than merely the first 6 or 8. The following story is about Gauss as a child. Now, the story is probably apocryphal, but it illustrates a point, and it's entertaining, and it's instructive, so I'm just going to go ahead and tell you that story, okay? Now, Carl Friedrich Gauss, if you're not familiar with who he was a German mathematician. He was born in the late 18th century, active during the 19th century, and we've already talked briefly about Riemann. Riemann was his student, so his younger contemporary. Gauss is known as the Prince of Mathematicians, and behind Archimedes and Sir Isaac Newton is oftentimes regarded as the third most significant mathematician, especially in Western history, okay? Like I said, he's also the teacher of Bernard Riemann. So, as the story goes, Carl Friedrich Gauss, can you imagine being his math teacher? His math teacher was getting really upset because Carl got everything much, much quicker than everybody else, and so he was doing what little boys who are bored in class do all the time. He was causing trouble. And so his teacher, deciding that, I forget whether it was a he or a she, but we'll just say she for the purposes here. She was like, I need to shut this kid up. So Carl, add all the numbers up from 1 to 100. And she's like, oh, well, that's gonna be really easy to keep him quiet for a while. Lo and behold, very, very quickly, Carl had actually come to a solution. And I'm gonna show you how he did it, okay? Now, 1 plus 2 plus 3 plus ... I don't want to actually list out all of those numbers, but if I sort of add that little ellipsis in the middle, basically that represents the sum of all the numbers from 1 to 100. But what good old Carl realized is that since addition is commutative, this sum is the same as this sum, right? Which is basically the same numbers just added up in reverse order. But if you do that, notice that if you add this sum to this sum, and you do it term by term, you get 1 plus 100, 99 plus 100, 2 plus 99, 3 plus 98, and all of those sums wind up being 101. Oh, sorry, 101. So but you know that there are 100 terms, right? And therefore this is lots of the same addition, and one of the uses for multiplication is to represent lots of the same addition. So 101 times 100 represents this sum. And that's really easy, right? So basically what you have here is you have 101 times 100, and that's going to be 10,100. But that is not the sum of all the numbers from 1 to 100. That's twice the sum. And so what you really need to do in order to get the sum of all of the numbers is just simply divide it by 2. And that will give us 101 times 100 over 2. And what that winds up being is 5,050. Okay. Now, you're like, okay, well, I would never, but that's just one instance. Yeah, but it basically can be sort of extrapolated out into a more general principle, and that general principle is the fact that anytime you have a series from 1, and it has to start with 1, to some number n of I, right? And the fact that it's I without a coefficient basically ensures that it will be successive integers, right? Successive whole numbers. That is going to be n, which is your 100 up here, right? Or actually, yeah, n is your number of terms, right? That's your 100. N plus 1, that's the 101, divided by 2. So anytime that you can actually get something in this form, that's great. So really what happened here is instead of n, it was 100, right? And therefore it was 100 and 101 over 2. But it could have just as easily been 6 or 36 or 1,600,542. It doesn't really matter. This formula right here will always work, okay, if it has that form. And you're thinking to yourself, wow, that's pretty neat. Okay, but that's just for things that look like a linear. If they look a little less linear, does that mean that I can't use a formula? And thankfully the answer is no. As long as it looks like a polynomial expression, I squared, I cubed, I to the 4th, you can use a formula. And I'm going to show you those formulas here in just a second. They're on the following page. I did not calculate these out, okay, but I'm going to show you all the way through I to the 8th. Now, Stuart, your textbook writer, and me, your teacher, we will only ask you to calculate up to the 3rd power. But I think it's instructive to actually see more than that. So here they are. Now, you need to know, as I was just saying, you need to memorize this one. And remember, guys, I don't ask you to memorize much. So when I ask you to memorize, that means something, okay? You need to memorize those 3. But for our purposes right now, what I want you to focus on is if you were to take this expression and turn it into n squared plus n over 2, and then the first term would become n squared over 2. This is going to wind up being 2n cubed plus 3n squared plus n over 6, and if you were to separate the fractions, your first term would simplify to n cubed over 3. This is going to wind up being n to the 4th plus 2n cubed plus n squared over 4, and if I were to pull it apart, that first term would simplify to that. Do you notice anything similar? You notice a sort of similarity in pattern to what we were doing in terms of the power rule for antidifferentiation. I becomes n squared over 2. I squared becomes n cubed over 3. I cubed becomes n to the 4th over 4. I to the 4th becomes n to the 5th over 5. I to the 5th becomes n to the 6th over 6. And I hope at this point you're starting to recognize the fact that it's add 1 to the exponent and divide by the new exponent. And it is true all the way down. Okay? Now you're starting to see how the sigmas are going to wind up relating to the process of antidifferentiation that we have already discussed. Okay? Now, we will, in the next video, actually get to doing some calculations and actually using these formulas. I think now is a good place to sort of break between the first and the second video. So, if you have any questions, as always, shoot me an email, and I will see you in the next video. Bye.